Okay, good morning. I'd like to take a couple minutes to introduce the American Chemical Society student chapter. I'm the faculty advisor for this, and we have two organic chemistry veterans to tell you more about that, Danya and Sophia.
Okay, hi guys, my name is Danya. I am a junior biochem major, and I took Orgo 1 last fall, so that was fun. But I'm here to talk about our American Chemical Society Club. So basically we're a club that gets a little bit involved in the community. So we go around to different elementary schools and we do little demonstrations using these statistics.
And then we'll add you all to the group where we use that. And follow us on Instagram, that's where we post all our updates as well. Thank you for having us.
Thank you all.
Okay, thank you.
So basically what we do is we teach the little elementary students a little bit about basic chemistry facts. So it's nothing crazy. We're not going to be teaching them about resonance or anything insane. But we teach them basic little concepts, and it's super fun, and it's a great way to get involved. It's also a great way to get volunteer points and kind of get to know your Dr. Donahue, our sponsor.
Yeah, my name is Sophia Schmidt. I am a biomedical sciences major, but minority in chemistry, and we're the co-presidents of ACS. We've seen some of y'all already in other classes that we've gone through, but for those of you who don't know about ACS, we do those demos like Danya said, and if you can't go to the demos, we also offer, so with every demo that we do for the elementary school kids, we give them this little bag that has magnetic molecules and a little pin and this activities insert. So if you can't go to the demos, you can also volunteer to do these molecules. All you do is glue magnets in them. Shouldn't take that long. So that's also an option to get volunteer hours and get involved with ACS.
ACS is also a great way if you want to become a leader. So I know a lot of you guys are in Orgo because you're pre-something, pre-graduate school, pre-med, pre-health. And you know a lot of those things, even if you're just like pre-employee. So like the job market right now is kind of crazy, so you want to be a little bit more competitive and you want to get those leadership opportunities. So it's one of those clubs that if you're really involved and you're active in it, it's really easy to become president, vice president, secretary, whatnot. And that'll look great for your resume. It's also, again, as we said several times, great way for you to build up volunteer hours by either showing up to the demonstrations or making these little things.
And one thing we want to focus on this year as well is mentorship. So a lot of the executive board, our juniors and seniors, and just ACS members in general, juniors, seniors. So I know a lot of you are probably sophomores, so we talk to freshmen as well. So if y'all need help with any of your classes or just mentorship overall regarding if you want to go to a research lab or internships or just what to do in the future, it's a good way to do that. We'll also have meetings where we talk about just professional opportunities. We'll try to work on creating a LinkedIn profile, getting that resume, personal statements, all those things to get you very prepared for graduate school or just any further education. We have profit share this on Thursday, yeah, right there. So it's on Thursday, all day at Montpellier, which is right in front of campus, right in front of the main entrance of campus. We'll have a social time from 6 to 8, so if you want to go there to just meet us and talk a little bit about what we do or just how to get involved, that would be a really great way to do that. And also support our cause, which helps buy money or materials to make these kits and also buy these items. And that's also our GoFundMe if you want to donate to that cause as well. So,
And the last thing we want to kind of talk about is there's a study abroad opportunity this coming January. So it's 2 weeks you'll spend in England. It's to learn about the history of chemistry, and it's led by Dr. Broom. It's a great way to get a chemistry credit, and it's also a great way to learn a little bit about chemistry. Any scholarship you have that spring semester will count there in England. So if you have half tuition off over there, you'll have half tuition for that course. And yeah, so make sure if you're interested in studying abroad, you reach out to the study abroad department because the deadline for that is September 20th.
Also, our first meeting is next week, aside from professor, next week, September 5th at 10 or 11. It'll be at 4, and we'll make slides and also just introduce the events that we have for the semester and get to know the executive board and just get to know each other as well. So we expect to see a lot of y'all there, hopefully. And if y'all want to join, I think we have the QR code for the membership.
Okay, any questions before we start the lecture? Questions for officers?
If y'all have any questions, join the group me and DM us.
Yeah, you can just message us on Instagram as well.
Yeah.
Okay, so last week I promised that we would go back to the beginning, and so here it is, the periodic table. You should all be familiar with this from general chemistry. I'll just point out a couple things, a couple of numbers that we want to keep in mind in terms of understanding the rules of building molecules. So I like to think of building molecules as a game, and there's some rules to the game that we have to follow, and it's basically the octet rule. And so I've used this term neutral bonding pattern. We'll talk about that, and then we'll talk about when things get charges, why do they get charges, and how do you calculate those charges. So we're really focused on only a select group of elements on the periodic table. So as just a brief refresher here, so periods run horizontally, so left, right. So that's a period. Again, think of the word periodic. So things are repeating. There are some trends to it. So you see the number 1 here on the left. So that is period 1. And then groups are up and down, so they're vertical. So things will change as you move across left to right. But when you go up and down in a group, the chemistry of those elements is similar. So for example, on planet Earth, life is made of carbon. Computers are made of silicon. So that's kind of interesting to think about. So both organisms, in a sense, sort of think. So as you're running across, if you look at the group numbers, so you have group 1, 2, so those are metals. We'll talk about metals in this class when we get into acid-base chemistry because we need cations, so positively charged ions, to balance out negatively charged anions. And again, more of that later on. We're going to skip across 3 to 13 there, or 3 to 12. That's the transition metals. So this class is not about those type of metals. Then we get over to, see how it says 3A or 13? I just typically use 3. So 3, 4, 5, 6, and 7. So 4 is what we're really concerned with, and that's where we see carbon. So period 2, group 4. And see the the bolded number there? So that's the atomic number. And if you look down into the table, we have element electron configuration. So if you go to carbon and then electron configuration, you see this 1s2, 2s2, 2p2. So those superscripts are the number of electrons in those orbitals. And what does that add up to, the 2's there? 6. So the atomic number is equal to the number of electrons for that element. And that's what we're going to use to do the counting when we start drawing Lewis dot structures in our understanding of the rules of the game to get to the neutral valence pattern. So atomic number is equal to the number of electrons. So you can see 6, 7, 8, 9, that's CNOF. So one thing I want to point out in going from electron configuration down to group, so carbon's group 4, and that's helpful because, if you look at that electron configuration, it's 1s2, 2s2, 2p2. When you're doing Lewis dot structures, you do not consider the core electrons. So we can basically forget about the 1s2. And so that leaves us with 2s2, 2p2, that's 4 electrons. So those are the valence electrons. And those are what are used in the bonding patterns to get to the octet, or the Nobel gas configuration, if you remember doing that from Gen Chem. So the next row here, we have valence electrons, so that's 4. Again, we're not considering core electrons. Now in this next column, it says number of bonds, neutral valence. So these are when we're just drawing and there's no charge. So carbon is probably the most straightforward. See how it's 4, 4, and 4. You have 4 valence electrons. It forms 4 bonds. And so what it's going to do is bond with 4 other things. Each of those things supplies 1 electron. That gets you to 8. And so the final row there, number of lone electron pairs, carbon 0. And then as you move over to nitrogen, we have 5 valence electrons, so that's an odd number. So what happens is the neutral valency for nitrogen is 3 bonds and then 1 lone pair. So how does that look? If you remember, that's how we would think of carbon. Now nitrogen, there's 3 electrons, and then the final 2, we just make a lone pair. And so then it decreases to oxygen because now we have 6 valence electrons. So going from N to O, one of those odd electrons gets paired, so we have 2 lone pairs. And then 2 unpaired electrons. So that's your 2 bonds, 2 lone pairs. Going into the halogens now, we're adding another electron. So one of the unpaired electrons gets the second one. That's the 3rd lone pair. And then you have the unpaired electron, which can form a bond. So number of bonds, 4, 3, 2, 1. And again, this is the neutral valency. So as we start painting this picture, when I talk about charge stuff, that'll become more clear. And then we use a little formula to calculate what the charge will be if it needs a charge on it. So what we're going to do in this slide here, this exercise, is just start building some molecules. So the top of the slide is the table from the prior slide. And it says we're going to add H dot, or H electron. So that's hydrogen. And so I'll show you through here what the thinking is. Put in those electrons above the element. And so now wherever there's a free or unpaired electron, you're going to stick a hydrogen by it. So hydrogen has 1, so it's going to get 1 hydrogen. And so that's how it's taught in general chemistry, right? You're taking those two together, you're pairing it, that forms a bond. So remember, one bond has 2 electrons. In the way that we represent the bonds in organic chemistry is just with a line between the 2 elements. So that's how we're communicating that. So carbon's going to get 4 hydrogens. So you can't really draw, this compound's called methane. You can't really draw it other than that. So, I mean, so that would be methane. One thing I do want to point out, again, we can't learn everything at once. So we sort of learn a concept, we learn some more, and then we revise what we've learned. So the way this is drawn is not spatially accurate. And I'll give you a preview of why. So these are the kits we use to give demos. I like these kits because they come together with magnets. You don't have to worry about putting bonds and holes. So this is a carbon. It's in the color code of elements for organic carbon is black. It's a sphere, there's a flat surface, and there's a magnet involved. So I put a hydrogen on 2, 3, and 4. So as you can see, when I move it around, like the way it's drawn on the slide, see how the H carbon H bond angle looks like it's 90 degrees. So in reality, it's not. It's a different bond angle. So HCH. We'll talk about how the bond angles change based on the number of sigma and pi bonds to the element. But keep in mind that we're drawing it that way because we're learning, but we're going to revise it down the road. So that's methane. So ammonia. Gets 3 hydrogens. And again, what I was talking about, the way I drew that, it looks like it's a 90-degree bond angle, but in reality, it's not. Water, we all know, is H2O. So again, when I'm drawing on the screen here, I'll put the lone pairs on the heteroatoms, but on the pre-made slides, you won't necessarily always see them, but they are there. And then finally, fluorine gets 1 hydrogen, so hydrogen fluoride. And so what those are, aside from hydrogen, those are 4 classes or functional groups that we'll encounter. So again, the functional group is just a discrete collection of elements that are present in larger molecules. So methane, ammonia, water, and hydrogen fluoride. Pretty much every other functional group you learn in this class will be a derivative of those. And so here are those structures drawn in for you. let's focus on the last row there that says determining dipole moment. And pretty much one of the top 3 answers you can give for a question in this class is going to be electronegativity. Why does a reaction take place at a certain carbon? It's going to be most likely electronegativity. And so let's look at those 5 molecules. And in light gray, I have written some numbers. And that's the Pauling electronegativity scale. So let me put in this CNOF ClSPSi. Fluorine's the most electronegative. So what I remember is that electronegativity increases across the period and then up the group. So hydrogen is a diatomic molecule. Both elements are H. The electronegativity is 2.2, so they're both 2.2. So hydrogen is considered a non-polar molecule. So when we're looking at functional groups, what that's informing us is based on the bond dipole moment, which is the difference in the electronegativity of the 2 elements. How do those bond dipole moments come together to give you a molecular dipole or the overall polarity of the molecule? So we have methane, CH4, carbon's a little bit more electronegative, 2.55. Hydrogen's 2.2, so this is also nonpolar. I'll just say NP. Now when we get to ammonia, nitrogen's 3, hydrogen's 2.2, so there's a difference between those if you just subtract those numbers. And so what is a dipole moment? So we can represent it 2 ways. Nitrogen being delta minus, and we know that because of this lone pair of electrons there. So that's electron density. So if that's delta minus, the hydrogens have to be delta plus. And so each one of those NH bonds will have a dipole moment, which is a vector. Those 3 vectors add up together to give you a molecular dipole. So how do we draw the dipole? It's going to be an arrow that points towards the delta minus. So in this bond here, sort of the plus part of the arrow is the delta plus, and then the arrowhead is pointing to the delta minus. So all 3 of those bonds have that. And then if you think in 3-dimensional space, they'll all add together to give you a molecular dipole. So oxygen is 3.44, fluorine is 3.98. Again, we're not getting down to nitty-gritty decimal points in this class. I just think of it as 4. So carbon 2.5, hydrogen 2, nitrogen 4, that sort of thing. So I've filled in the rest of this table at the bottom of the slide here with some physical properties. And what you want to start, the intuition you want to develop is looking at a functional group, figuring out dipole moments based on electronegativity, and then ultimately how does that inform you on polarity, and then how does that affect the physical properties of the molecule. Again, let's just take water. So there's water in here. So the melting point of water is 0. So every temperature measurement we use in this class will be degrees Celsius. So when the weatherman reports the weather, that's degrees Fahrenheit. So water is 0, it boils at 100. So that's nice, right? It's 100, so you have these individual degrees between there. 25 degrees, which is ambient or room temperature. Water is a liquid. Its dipole moment is 1.85, and even though we call it water, because it has the OH group in this class, we'll call it an alcohol. So what you want to think about is, structurally you have water. It has those physical properties. And then if I draw a line here, what makes hydrogen and methane so different in terms of their melting and boiling points than these other compounds that have heteroatoms, and a heteroatom being anything other than carbon or hydrogen. So you can see that, these things get pretty cold. So what is 0 degrees or 0 Kelvin in Celsius? Do you remember? Negative 273, thereabouts. So when you think about, there's these different scales. If there's no heat, you're at 0 Kelvin. And then from that, you're adding heat. And then for each molecule, you're going from solid to liquid to gas. So there's these phase transitions. How do the functional groups affect the phase transitions? So we'll get into more of that probably Wednesday or Friday. So one of the rows I did not have filled in there was the molecular weight of hydrogen, methane, ammonia, water, and HF. So again, this is taking the molecular formula and converting it to the molecular weight. So using the atomic mass units. That's the other thing I wanted to clarify real quick. Again, atomic number is number of electrons. Atomic mass are these mass units. So H2, if hydrogen's 1, we can eliminate choice A. So now we're at methane. Carbon is 12. Hydrogen's 1. We have 4 of them. We can eliminate D. Nitrogen is 14 plus 3. That gets us 17, so we can eliminate B, and so C is our correct answer. I know that's sort of straightforward in a way, but it's going to become important, again, as we move into Module 2 and we learn about mass spectrometry. You're going to have more complex molecular formulas you have to do that for. Any questions? So there's the table fully filled in. One thing I'll emphasize, the attendance quizzes, the exams, everything's multiple choice. The classes are way too big for me to hand grade anything, so there's no short response. But say a short response question could be, the molecular weights of all of these are relatively the same. So why are their physical properties so different? So you can't say, well, this is 16 or that's 17. The weight of the compound does not really affect the physical properties. It's the functional groups that are present. And so we'll talk about interactions like hydrogen bonding, so non-covalent interactions that affect physical properties. So on this slide, we're gonna now build up using that. So a carbon with one open valence. And so we're going to do that same exercise with this first row here. So this is equivalent, if we were drawing it in the Lewis dot form, we're going to take that fragment and then bond it to whatever you see in that first row. So that one carbon unit with an unpaired electron bonded to a hydrogen, we've already made that, that's methane. So moving forward, I'm just going to represent the bonds as lines. I'm not going to draw the two dots between the elements. But again, the line means those two electrons, where each element is supplying one electron, as we saw from the periodic table, as the atomic number increases. So if we take the carbon situation now, which is basically that plus that, so that's what we're doing. And we form a bond between them. So we now make this molecule. So that molecule is called ethane. And so notice the ending ANE. The functional group family that's a part of is called misspelled here, AL. I've taught this from these slides for 3 years, and not one student has pointed out that mistake. ALKANE. See how they both end in ANE? So that's sort of like your surname, your family name. When we learn about these functional groups, they'll end in a common name. So if something ends in ANE, it's going to be an alkane. And that means it only has carbon and hydrogen in it. So those are things that when you see that, you have to infer. So here are our two alkanes, methane and ethane. Now if we take that carbon unit, we bond it to NH2 dot. We get this CH3 NH2, and that's called an amine, AMINE. So it has one carbon, and its name would be methanamine. So one of the things, again, one of the learning outcomes for Module 1 is understanding a name and what functional group is present. The next one, moving across the periodic table with oxygen, we now have methanol. So see how it ends in OL? That tells you it's an alcohol. The first part of the molecule there, when I've drawn the line methane, that tells you there's one carbon. So some of you might have partaken over the weekend in that molecule. What do you think that's called? Ethanol. So this alcohol right here, you have one carbon, two carbon. So 2 carbons is ethane. So the 2 carbon alcohol is ethanol. No matter what your poison is, beer, wine, vodka, whatever, that's the alcohol in that. It just tastes different the way it's made or fermented. So you drink ethanol, you do not drink methanol. If you drink methanol, you will go blind because this gets metabolized in your body, and then it reacts with a nitrogen group in your eyeball. It forms a covalent bond that doesn't let the enzymes move a certain way. So it's interesting that just adding one carbon makes the difference between a life-altering healthcare issue and having a good time on Saturday night. And then finally, hydrogen fluoride fluoromethane now. This is called an alkyl halide. And so those are the first couple functional groups that we'll learn. And again, the bonding pattern. Alkane is just CH with all sigma bonds. An amine has a carbon-nitrogen bond. An alcohol has an OH bond. And then an alkyl halide is going to have some sort of halogen in it. So we've drawn those. Here's the summary slide showing the electronegativity differences. I'll draw the line in showing you the difference between polar and nonpolar. Question? So it's fluoromethane is named as a derivative of methane. Again, probably one of the pain in the ass things in this course that you will find is even though there's rules, there's like historical things that just don't die. So we'll call those things by many different ways. So when we get to the nomenclature rules, we could also call that methyl fluoride. So it's just different ways of communicating the same thing. So here's the line. So these are nonpolar. These are polar. And the line is there again because you have N, O, and F, which are those electronegative heteroatoms that give polarity to the carbon bond in overall molecular dipole moment. So this sums up the term electronegativity using the Pauling scale. The dipole moment, which is the Greek mu, shown there. You don't have to worry about calculating that or figuring any of that out. It's just very qualitative based on, things increase towards fluorine going across or going up. Your book will typically show you this little table here to the right. Those are the electronegativity numbers. When you take the difference, if it's less than 0.4, it's nonpolar. If it's somewhere in between that and 2, it's another mistake. It's polar. I'm going to cross out the non there. If it's greater than that, what do you think the name is? Or the compound class? If the difference in electronegativity is greater than 2. What'd you learn in Gen Chem mainly? Ionic compounds. So those are things like Na plus, Cl minus. We will talk about ionic compounds in this class. You see how the chlorine's negative, so that's a formal charge. I'll show you how to calculate that. It should be sort of intuitive by now based on Gen Chem. You have this cation to the left, this anion to the right of the periodic table. They have to come together with charge that balances out, so plus minus equals 0. So here are the physical properties of those compounds: methane, ethane, methanamine, methanol, and fluoromethane. Again, I would say think about methanol. See, its boiling point is about 65. How does the collection of the OH elements in that alcohol functional group affect the physical properties? So you see in the boiling point for methylamine, which was what Heisenberg was stealing. Anyone watch Breaking Bad? So they stole a whole train tanker car full of that to make what? Methamphetamine. So if it's a gas, how are they stealing it? Well, the NH2 group adds polarity. The polarity helps dissolve it in water, and so they basically stole a solution of water to build their meth empire. So you'll see how, just the presence of those lone pairs changes polarity and how things are soluble in different solvents. So this slide is based on some poem whose name I have since forgotten over the last 10 years. But basically, from the atomic level, the electron configuration, all the way up to the molecular level, the electrons matter in terms of how they form bonds and what functional groups they're in. Then the properties of the molecule on scale. So, water is, I swirl it and it moves in this container, right? So, there's things like viscosity and that. So from the molecular scale to the bulk scale, it's all connected. And that's the intuition you want to develop, again, by just looking at a structure. So in this slide, what you can do on your own time is draw the compounds. So for example, if you take H dot plus this H dot, that gets you hydrogen right here in that first column. The second one, you'll make methane. The third, ethane. The fourth, propane. And what you're just thinking about is, okay, this is the melting point, that's the boiling point. The difference between them is the range. So you have these phase transitions. They go from solid to liquid to gas. And then as you move across to these other functional groups, so FG, functional group, going from H to NH2 to OH to F, how do those numbers change? How does the melting point change across that row or down the column? So you're moving across, you're changing the functional group, but when you're moving down, what you're doing is adding more carbons. How does that start to change? When do things become a liquid at room temperature? Again, we'll talk more about this in Module 1 as we learn about why these things change. Why does a boiling point change so much if you have an OH group at the end of the molecule versus when it's in the middle of a molecule? What factors are affecting that? Any questions? So here is what I think is the fun part, but everyone has their own definition of fun. So to me, this is like a game. You have these building blocks, you need to put them together, and as we progress down in carbon count, so we're going to talk about alkanes. So remember, things that end in A-N-E are a functional group. They're called hydrocarbons. So C plus H only. Hydrocarbons are harvested from petroleum, which is a pretty important economic sector here in the Gulf South. So crude oil is many things. It's many constituents. And so within that are all these different hydrocarbons. Alkanes have a molecular formula of CnH2n plus 2. So where n equals 1. You plug that in there, that's going to get you a molecular formula. That formula can then have different compounds associated with it. So for 1, 2, and 3, you can only draw one molecular formula. So methane, ethane, and propane. However, when you get to n equals 4 or above, the molecular formula can now produce more than one compound. Do you remember what that concept is called? You have a molecular formula, but it can be different structures. So isomers, we'll talk a lot about isomers in this course. This specific example, they're called constitutional isomers. So for one molecular formula, the elements can come together in different bonding patterns. So the question is, if a molecular formula produces more than one compound, how can you tell them apart? So the first column is carbon count, 1, 2, 3, 4, 5, 6. So we have methane, CH4, ethane, C2H6, propane, C3H8. So again, that's the CnH2n plus 2. What I want to highlight is butane. So butane's the next thing up, but notice I have a second entry for it. And then I have these physical properties for two different compounds. And then pentane has 3 entries. Hexane has, 5 entries? Before we move into butane, how do you calculate the molecular weight for methane, ethane, and propane? So CH4, C2H6, C3H8. I think we already said that methane was 16, right? So we'll eliminate B and D. What do you think the weight for ethane is? 30? So if we take C2H6, CH4, and I'm going to do organic chemistry math. So if I take the molecular formulas and subtract them, I get CH2. And so what is that worth? So 14. So as you go up in these methane, ethane, propane, butane, the difference is always going to be 14. So these are called homologs because all you're doing is adding a CH2 group as you move from one to the next. So the answer there is going to be C. So take a look at the last column there in green. So I have this thing, C13, 1H, and then ratio, and then I have these numbers for each. So here's methane, ethane, propane, so for methane, I have 1, 1, and 4. Ethane, 1, 1, and 6. Now propane's a little different. 2, 2, 6, and 2. Do you see any sort of way to explain that? The first number says C13. That's the number of unique carbons in the molecule. Methane only has 1, so that's got to be 1. The 1H is the number of sets. Sets of hydrogen. And then the numbers in the parentheses are the ratio of the hydrogens in those sets. So there's only one type of hydrogen in methane. All of these H's are the same. So that number ends up being 4. When we get to ethane, see the molecular formula has 2 carbons, but I'm only saying there's one type of carbon. Why is that?
Because they both serve the same.
Say it again.
They both serve the same function.
So there's a symmetry about the carbon-carbon bond. So I'll draw that in blue, just as a line. So that line represents a mirror plane. The left-hand CH3 looks like the right-hand CH3. So even though there's 2 carbons in the molecular formula, there's only one type of carbon. There's 6 total hydrogens. There's 1 set of hydrogen, and it's the total 6. All of those hydrogens are the same. Now, propane is different. It's 2, 2, 6, and 2. How do you make sense of that? So the terminal carbons at 1 and 3 are the same. The central carbon, CH2, is different. So the mirror plane now bisects that actual carbon. So that means you have 2 unique type of carbon, 2 sets of hydrogen. So this number 2, within the parentheses, you have to report whatever number is outside. So I have 2 sets, so I have to have 2 numbers in here. And what does that total equal? 6 plus 2 is what? 8, and so that's 8 hydrogens in the molecule. And so the reason we're doing this is because now when we get to C4, butane, there's more than one butane. Or excuse me, let me rephrase that. There's more than one molecule with that molecular formula. So as shown here, for 4 carbons, we have C4H10. One molecule is called butane, but there's another molecule that can be made with 4 carbons and 10 hydrogens, and it has a different name. So we have C4, H10. So there's 4 carbons. I just drew them in a line. If I put in the hydrogens, there they are. So how many unique type of carbons does this molecule have? So 2. How many unique sets of hydrogen? And so I need to put in 2 numbers there. What should they be? 6 and 4. So remember last week we talked about carbon and proton NMR. This is essentially what you're learning to predict or interpret. So when I say a unique carbon or a unique set, that's what the carbon NMR of butane is going to show 2 signals. The proton NMR will show 2 signals with a ratio of 6 to 4. You have a question?
Yeah, how do you get the numbers in parentheses? Like, can you explain that?
So these 2 numbers here, 6 and 4. 1, 2, 3. This is equivalent. 4, 5, 6. Carbons 2 and 3 are equivalent. 1, 2, 3, 4. So how, C4H10, how can we make another molecule of that? And the logic in this, I'm going to call this linear. So you have to drop down. The molecular formula is still the same, C4H10, but now you're going to subtract off 1 carbon of the longest branch. So instead of drawing 4 carbons in a line, we're just going to draw 3. That leaves us 1 carbon left over, right? So carbon 1, carbon 2, carbon 3. We have 1 more carbon. Where should we put it? Carbon 2. So now you put in your hydrogens there. And so that's the same molecular formula, but now it's a different compound. This is called 2-methyl propane. And I'll talk about how we figured that out, but what I want to wrap up on with our last couple seconds here is how many unique carbons does this have? It has 2. So even though this group right here is drawn up, it's still equivalent to carbons 1 and 3 because it's bonded to carbon 2. How many unique sets of hydrogens does this have? 2 as well. And then what numbers should go in the parentheses? 9 and 1. And so that is a method that we're going to use when we have a molecular formula that can make different compounds to distinguish between them. And then I'll show you how we actually go through the nomenclature as well. So don't forget to do your quiz. It's open for 24 hours.